Do you want to? Beautiful.
Yeah, thank you very much for the presentation, Bernardo. I thank everyone to be here. So my talk is something that starts last year. It was just a problem that I put it to a student that he was just in the bachelor, and then he solved very well. He is Emilio Dominguez from Sinaloa, yeah, Culiacan. He now is going to be doing USA, making the PhD. And well, that's the problem, and after come a lot of them. So let me give you some antecedents of this, what we are going to, what we studied. We start with the usual free-oriented G-Bordis group from Conor and Floyd. So all there are free covariance classes of n-dimensional manifold up to G equivalent bordings. And suppose that we have the bordines, but a little suitable modified that you take n+1 dimensional manifolds with a G axion, but not necessarily inside the manifold free. But in the boundary, we are going to take that the axion is free. And take the canonical map that assigns to every, restrict to 3-dimensional manifolds with boundary. The axion is free in the surface, and acts as boundary, and take the canonical map to the boundary. And with the Bernardo came to Oaxaca with this question, and he asked me, well, is this true? Is this true, this question? And I didn't know the whole story behind that this comes from really we put it this the free extension conjecture that this map is suggesting. But after this, I be aware that this comes from a whole conjecture called the evenness conjecture that for the not equivariant case say that it was proved by Miller and Novikov that the unitary Bordines group can be write as a free module over the just unitary of even generators. And this say that the G equivariant unitary Bordines group is a free omega module on even dimensional generators whenever G is a compactly group. So if this is free, then as in the free case, there are not fixed points, so everything is of torsion. So if the evenness conjecture is true, so the free extension conjecture is true. And then comes another, my student's name is Emilio Dominguez, and then comes another E. Eric Samperton comes and he writes me and say, well, I don't think that this is true. Well, and then we talk for a long time. And then he comes with a counterexample for a free group, a 3-phi group of order 243. And he proved that this group admits an axiom over a manifold that does things. Well, in this talk, I'm going to talk about, well, my work with Emilio. And we proved some cases in our article for, we believe that it was true, that the free extension conjecture was true, and then we proved the case for abelian groups, for diedrals, symmetrics, and alternated groups. So this is, and after I will talk about what's happening for the Coxeter group. So let me just say, in this is measured by the 2 free Bordines group, and this is something old that comes from the Schur, that was called the Schur multiplier, by the name by Schur, a mathematician from Germany. And nowadays, these represent three different isomorphic groups. These are the second Bordis group, the second homology group, and then second homology groups, the coefficient in C star. So, but the whole partition I will call the Schur multiply. And in the project, the original project that I put Emilio, I find a paper of Claire and Miller that if you check it in the Matsunet, this has a lot of sites, 50 sites, yeah. And she gave a way to see the Schur multiply in terms of generators. So she take the free group in all pairs of the group, and then he take the kernel that you send this group to the commutator group. So when you see as the axiom, they say that the surfaces are closed. And you take the kernel by the normal subgroup generated by these four relations. So the idea will be to give an interpretation in terms of G coordinates. So if you play with this, so this is really algebraic, but you will find that this has a really a geometric interpretation. So we are going to, when we give the exponent to x, it's just the conjugation. So we can play these algebraic settings, and then we can find a lot of identities. This you can find in the paper of Claire. So let me just put a point. Yeah, and then, well, let's give you a geometric interpretation in terms of coordinates, G coordinates. But what I mean by a G coordinates, well, we have the usual definition of a coordinate as a classes of triples, where this is the incoming boundary, this is the outgoing boundary, and there are the boundary, the union of these two manifolds is a D+1 manifold. And then we'll consider that two triples are equivalent. You can find a different machines that can satisfy this commutative diagram. So we can extend this definition to G coordinates, and then you take triples where each element is a principal G bundle. And all of this, well, we are going to assume that every manifold and surface are oriented, and all the promises are reserved in orientation. So if we can restrict to low dimensional cases, then we can see that any principal G bundle over the circle can be really easily constructed. You just take the product of the interval and the group, and then you glue the two ends just by the product of one element that you take as fixed. So this I'm going to talk is just the monodromy. I'm going to talk all the talk. And well, taking that, so any J coordinates over a surface is the gluing of elementary parts that are just principal G bundles over the cylinder, the paired bands, and the disk. So we can see that for the cylinder, they are given just by conjugation. For the paired bands, we are taking especially principal G bundles over paired bands, and they are just product of the monodromy. And for the disk, since this is contractible, so the only possibility is that in the boundary we have trivial monodromy. We are when the monodromy is assigned to the neutral element, we say that is trivial monodromy. And for example, for a handle body, yeah, we can just compose. This is very combinatory, and then the boundary has to be an element of the commutator group. So the monodromy associated to the boundary of every handle body is an element of the commutator. So as if we see the interpretation of the Chur multiply given by Clara Miller and by G-Coverdis, so how is the assignment? The assignment is just as follows. So you take an element, a sequence, in the free group generated by pairs, and then you assign the following G-Coverdis. Here, you start by the right, and then there are some identification in the G-Coverdis that I cannot say in this talk, but believe me that every G-Coverdis has this normal form. That you just, every genus depends on 2 elements of the group. That's it. And this is closed, and so at the end, the product of the commutator is trivial. So, and the assignment is you take the last element and you put it here in this generator, and then xn is the conjugation, and so on. No? So using that, we can give the interpretation of the generator of these 4 identities used to form the Chur multiply. For example, here, this identification, you start with this, and then you apply some dent twist, and then you can, find this. You get a trivial monodromy. And here, then you can put in the trivial monodromy because this is a trivial principal bundle. So you can fill it by this, and this extends to the total space, and then you arrive to a sphere, and you can fill it. So this is trivial. Also, the other generator is that you can, if you just invert the generators, then you have just the inverse in the Chur multiply. And this is just the following, so that this product is trivial. And this is just the following. Okay, here, if you remember when we had the handles, there are some identification I didn't say, that when you reinvert the generators, then you have the following identity. That you have G transform into the conjugation, and K transform into the element that embrace the genus. So using this, well, you can, here you will have, you can have X and then Y as the conjugation, and then you will have also here J and X associated to this pair. And you could here, you glue the 2 genus in order to form only 1 genus. And this has trivial monodromy, and we use the same idea. The other 2 identities, there are really, and they are the same process. Here we put Z, X is this, there are the generators, and then the other, just the conjugation of this is the conjugation of Z, the conjugation of Y, and then if you see the monodromy here, this has trivial monodromy, and then you put, and then you reduce the genus. And also the 4 identities. So in essence, we can see that the Chur multiplier of a finite group G is isomorphic to the group of closed G-Coverdis, where 2 of them are identified, and we can go from one to another by putting and capping along a trivial monodromy. So as a definition, we can say that a G-Coverdis over a surface is extendable if for some representative with the axiom given by the principal G bundle, there exists a 3-dimensional manifold with boundary the total space that extends the axiom. So taking this as a definition, so this is the most important property or result in this that we use. Any G-Coverdis over a closed U-base of genus 1 is extendable. And this is just given by, well, if you choose the 2 generators, so the conjugation, it has to be trivial because the commutator is trivial. So you have monodromy here, suppose an element G, then you conjugate, and then you have the same principal G bundle over a circle. And then, well, what happened? Well, we can choose just the number of circles and the degree of the map, and this is stands just in as a complex variable. This is just the rotation by some angle. And then, well, you feel this is a handle body, you feel this, and then you do two ends. So every G coordinate of genus 1 is extendable. So suppose the case of a finite abelian group. Well, there the commutator is trivial. So start with a G coordinates and put every between every genus. So you can separate all these parts, and all the G coordinates are of genus 1, and so they are extendable. So for finite abelian groups is almost evident that they are extendable. So, and well, I want to recall the results of Zimmerman, that he works for the case where the axioms are not necessarily free, and a result from him and Rennie was that suppose an axiom of a finite abelian group, not necessarily free over a closed orientable surface, where we have to assume something really that the ramification point of signature bigger than 2 has to come in monodromies in pairs. And this is the reason is because if you want some ramification point, and you have to have the another, but with the inverse, in order that you can do a handle that, and then you feel it. Yeah. Therefore, the G axiom extends to a handle body. And also, Rennie and Zimmerman proved that any axiom of a diagonal group, this not necessarily oriented, extend to a handle body. And also, all the axioms are preserved, orientation. So let's, for diagonal groups, but in our case, we take, let me explain, we take this presentation. The presentation is that you take two reflections, and you take C is just the rotation by to be quotient by N. Then yes, we can write the group as the following 2N elements. So for the other groups, the result will follow because we can just work really algebraically. And so the sequence of pairs in the free group generated by the pairs of elements of the group is equivalent to some product of the C, that is the rotation, and a reflection exponent to some positive integer. Well, not necessarily positive, it could be negative, for some element instead. And well, then we know that the commutator of the diagonal group is a cyclic group generated by C to the square. So this element will represent an element of the Schur multiply if only if this element is closed, in the sense that C to the 2L is equal to 1, and this happens only for L equal to N divided by 2. So this immediately proves that for N odd, the Schur multiply is trivial. And for the even case, this is zeta 2 because, well, we can prove that these two squares is trivial. So for the generator is given by the rotation and the permutation by elevated to exponented to the N divided by 2. So this is the generator. So, but it's a generator of genus 1. So by our previous theorem, this is extendable. And something happened really also similar for symmetric groups, because, well, we know that we can just do calculation for low dimensions, and for n less or equal to 3, this is trivial. For n equal to 4 is theta 2. This we did the calculation, and then we can prove that if two sequences that has the same commutator, then they differ by a product of some element that is the pair associated to the transposition 1, 2, and 3, 4. And this is the generator. So if we put that this implies, because of this is has u exponent to the square, and this is trivial, we prove that for n bigger than 4, this is the Schur multiply has to be theta 2. And this is also of genus 1, so every S n cover is extendable. For the alternated group, Emilio has really a clever idea, and he, well, the Schur multiply has these values. Therefore, for n big, less than 3, this is trivial. For n 4 and 5 theta 2, and this is an exceptional case. For 6 and 7 is theta 6, and then bigger than 8 or equal is theta 2. And we prove that this element is the generator, this pair of two transpositions. And the idea was that you include this in the symmetric group, and you prove that this is equivalent to the generator of the symmetric. So this gives you a non-trivial element, and because we know how is the Schur multiply, then this has to be the generator for n bigger than 8. For the other cases, there is really some result that you can find on paper, is that for a finite group, if all Silos groups satisfy the free extension conjecture, then G also satisfies the free extension conjecture. So for the alternated group A6 and A7, we have that these are the Silos groups, and they satisfy the free extension conjecture. So all the alternated groups satisfy that they are extendable. So now, well, the general case for Coxeter groups, then for that, this came really here, not so far, and we have to check what is the Bogomolov multiplier. So we have the Schur multiplier, and then we divide by the subgroup generated by one-dimensional theory. With that, is the same that we take the G properties of genus 1. And this is the Bogomolov multiplier. And this has a really long story, because something that really is amazing for me is that if this is trivial, then the inverse Galois problem solved for this group. Amazing. But this also, this multiply has really some properties very useful, because if you take the product of two groups, the Schur multiply commutes with the product. We know that a finite Coxeter group has a representation in terms of reflections, and well, this is just this is the presentation. But let me put some examples. So for example, the diedral group. Yeah, if you can take a Coxeter group, and this has a Coxeter diagram, and you put an arrow if this is bigger than 3. If this relation Ri Rj to the MEI is equal to 1, you put an arrow if this is bigger than 3. So if you don't have an arrow between two generators, there is an arrow of with m equal to 2. And there are loops, yeah, because Ri is they commute. Yeah? So so they are idempotent, so they are an arrows that you are not going to see in the Coxeter diagram, but these are the Coxeter diagrams stated to the diedral and for the symmetric group. And there is a really important result in this theory that say that all the irreducible finite Coxeter groups are given by these these 8 families. And also, there is a property that an irreducible Coxeter group, the diagram has to be connected. So we can take any finite Coxeter group and then we can just consider the irreducible ones. So there is a theorem that tells us how is the Shor multiply, and there are just abelian elementary binary groups. There are only powers of zeta 2. So let me say what is the idea for that. We are going to recall to this. So in essence, we will find, it is possible to find 2 types of generators. Diedrals, that you remember, we take the rotation, and by this is just the product of 2 different reflections, and we take one of the reflections. And this is, we are going to represent this by Ri and Rg, and with this curly, these are the 2 generators associated to some unions. And there are also symmetric generators. That is some elements that are far in the Coxeter diagram. So they are related by m equal to 2. And there is a theorem, well, that a result that you can find when in the papers of Ihara. Yeah? And we adapt to this case for the same type of generator, yeah? Because also in the jig for this, you plug it into the representations. They are the same only as conjugation, and the conjugation don't change these m's. So, and the identification is that if you have a pair Ri, Rk, if this is related by an arrow with m equal to 3, then this is the same as the Rj and Rk. And also this kind of movement is that if this is odd and this is odd, yeah, then this Ri, Rk is the same as Rj, Rl. So with this kind of movements, then, well, let's do some examples. For example, B2 is the diedral, but B3, this is the value for the Schur multiplies. And so for n equal to 2 is the diedral, and there was only 1 generator. So we are okay. For n equal to 3, we have 2 generators, and the 2 generators are the following: is this R1, R3, and R2, R3. And there's not any other identification. Why? Because the value of this arrow is 4. So the second relation, it doesn't apply. But, well, suppose for B4, what's happened? Well, you add this arrow, and then this is created, yeah, but it is not identified with R2 and R4 because this is even. And, well, you can also consider R1, R4, but this is identified with R2, R4. But let's assume the other interested case is when this decrease of generators. For n equal to 4, you have 3 generators, and these are the 3 generators. But when you put an additional arrow for D5, so this Yeah. What's happened, no? Well, you can, this is R2, R4, and this is this transfer to R1, R4, but then this transfer to R1, R3, and then this is the same as R2, R5. So remember this relation, this relation. Yeah? These are the two relations that you can transfer this to this and this to this, and using that, then R1, R3 transfer to R1, R4, and then R1, R3, and then to R1, R5. And well, that's it. So this proves that for every Coxeter group, every G over this is extendable. This is not, and also show that the inverse problem, the inverse Galois problem solved for Coxeter group. These are the reference, that this is the paper of Uribe of the evenness conjecture, the work of Zimmerman, the paper of Clara Miller, and also the result for the Coxeter group. And if you want to see the counterexample of Eric, and this is the paper when you can find all except the work with Coxeter group. Well, that's it, and thank you very much.
Carlos, thank you very much for your talk. Pretty enlightening. Let me first ask the audience if anybody has a question, comment. Please simply speak. Okay, let me just ask then some few questions that I wonder. From your talk, I learned, and I was not very much aware of it, that the second homology group of a finite group could be filtered by whether the class of the homology or the Schur multiplier, as we call it, is generated by a genus 1 surface or by a genus 2 surface or by a genus 3 surface, etc. Namely, any homology class has a minimum number of genus which generates it. Mm-hmm. The Bogomolov multiplier is all the classes that are generated by genus 2 or higher. But I suppose one can filter it by any genus, genus 2, genus 3, genus 1. My question is, if you have a group, could you distinguish the degrees on which the homology will be generated? Namely, it will have classes of genus 1, and it will have classes of genus 2, and perhaps a class of genus 3, or something like that. So is there an algorithm that is not calculating it by some sort of computer program? Is there an algorithm that could tell me what is the highest genus that is necessary to get all the homology, second homology of the group?
Yeah, it could be performing in a computer. I think.
No, but not in a computer. Something as you did. So because you have some sort of, you take any surface of genus N and you put elements of the group, and you have some algorithm to decompose it such that you may lower the genus. That's somehow the process you gave. You told us how to lower the genus until you are stuck and you cannot lower it anymore. So I was wondering if there is some sort of way to, from the group itself, to tell, okay, this is the lowest genus, or this is the highest genus that you cannot lower.
Yes, so the idea, I think the idea is to see the cover. That this was called by Schur the Darstellum's group, the representation group, and in there you have the commutator length. If you find the commutator length there, then these are going to be the genus of the lower genus you will find for your generator.
Okay, so if there are only classes of genus 2, then the commutator length is what? 1.
I don't think you can say, if you know the commutator length, I don't think that necessarily implies something for representing two-dimensional homology classes, because the commutator length is more about extending, if I have a map from a circle into the classifying space of G, and I want to know, can I extend that across a surface that maps into the classifying space? The commutator length of that circle, right, is basically an element of the group. And when you map the circle into BG, it's basically an element of the group. And the commutator length of that element is the minimal genus necessary to extend the map from the circle into BG to a map from a surface with boundary that circle into BG.
Wow, Eric,
So
you said so many words.
Sorry. Sorry.
You said so many things. Okay, say that again. So
commutator length is the following. I have an element of G. I can think of that as a map from a circle into the classifying space of G.
Good, yes.
Okay. The commutator length of that element is a minimal genus required in order to extend that map from the circle into a map from a surface with boundary that circle into the classifying space.
Okay, but using your argument, could not just one simply, for every element of the group, carry out this question and then?
Yes, but you're not looking at homology classes in H2. It's only when the map, you need to have a closed surface in order to have a map that represents something in the second homology.
These things are still with boundary.
Right. So it's more about saying, well, everything in the commutator group can be extended across some surface, but we're more interested in something like, well, when you have closed surfaces, what's the minimal genus of something homologous to that closed surface?
Exactly. So somehow that was my question, and I thought one could algebraically try to answer it using this procedure of Carlos. Somehow, the one you said is you take something in the commutator and you can just get a tori with a hole, isn't it?
Yep.
But then you need to glue this tori with two holes to see how you finish it. So I thought one could perhaps cook up a procedure to determine.
I think you want to do something similar, but like there might be a way to cook up such a procedure using the hop formula for the second homology. Is that what I want? Hop's formula? Yeah.
But it's the one that is a very algebraic using elements of the
yes,
group.
yes, but I think you could probably interpret in terms of some cover, or in terms of some other group. Basically,
Okay,
commutator length there should give, and some other associated group using Hop's formula should give.
But I was wondering that maybe it could be said maybe in the covering group. We find the covering group and then we study the covering group. And then with that, maybe we can say something about the minimum genus in terms of the commutator length or something like that.
Yeah, maybe.
Yeah. And
so Carlos, in what you calculated, you showed that the Bogomolov multiplier of all Coxeter groups is trivial.
Yes.
If I understood well.
Yeah.
Okay. Okay. So Eric and Carlos tell me. So the groups on which, and I think there is Professor Moravec around somewhere. So the groups on which the Bogomolov multiplier is not zero, besides being complicated or interesting P groups, what there is else? Eric, do you know, Carlos? Well, I know P groups, but is there anything that is not a P group? Or just built out of a P group and I just glue it around because in the P group it has no Bogomolov multiplier?
Yeah, we thought that maybe the complex reflection groups could be a counterexample. Yeah. also of the Greek extension conjecture, no?
Okay.
There's a couple of weird complex reflection groups.
Mhm.
I forget which ones. I don't really know much about these things that I expect will have non-trivial Bogomolov multiplier.
Yeah. I don't know. Maybe Moravec is here and you can say something.
But certainly you can find P groups with non-trivial Bogomolov multiplier.
Yeah, that here is
Hello.
Moravec. I know. Hi.
Hello,
Hi,
Moravec.
how are you? So I was kind of, nice to see you all. I was listening to a discussion. I wasn't able to understand everything, but I think if you're talking about the commutator length, I think if you compute all the derived subgroups of cover groups are always isomorphic to this Miller construction. So that means that if you take any cover group and compute the commutator length in that group, that should give you the commutator. And then you take an element in H2, that should give you, so the commutator length of that element is going to be precisely the same as the commutator length in the derived, in the cover group.
Yeah, exactly. Yeah. So the commutator length in the Schur cover is related to the minimal genus representative.
Yeah.
That's what it is. Yeah. So if you have your group, you take a universal central extension.
That's right.
And commutator length there is related to minimal genus representative of the homology class.
And also, if you take the Hop formula, you have this free presentation of your group, and then you take the derived subgroup of, you take this F over the commutator of F and the relation subgroup. And if you take the derived subgroup of that one, that's the same as Miller's group. So either way, you can do it either in the cover group or in this universal extension, as you're saying.
Good.
And also this Moravec, there is a some group that is not a P group that has not trivial Bogomolov multiplier.
Excuse me, I didn't hear the question.
Is there a group that is not a P group that has not trivial Bogomolov multiplier?
Well, if you just take a direct product of some P groups for distinct primes, and then by your formula, the formula you mentioned, the Bogomolov multiplier is just a direct product of Bogomolov multipliers of components. So that should give you some.
Okay.
There are a couple of weird central extensions of PSL3-4 as well.
Okay.
Maybe on the more, more exotic, further away from P groups, you can look at non-solvable groups, and there's a couple of weird extensions. Yeah.
If you take something like a simple finite simple group or quasi-simple, then they all have trivial Bogomolov multipliers, but I'm not sure about.
Well, no, except for these two examples of PSL3-4. All the quasi-simples have trivial Bogomolov multiplier for a couple of those. So there's a paper that defines Bogomolov multiplier. I forget the author, Kunyavsky,
I think, yeah.
I think the original preprint claimed that all quasi-simple groups had non-trivial Bogomolov multiplier, but then in the published version, he realized there's these two weird counterexamples that come from covers of PSL3-4. Somehow PSL3-4 has an absurdly large Schur multiplier. It's way bigger. It's kind of it's exotic because its Schur multiplier is very big. Typically simple groups have very small Schur multiplier.
Interesting. Well, what is the answer? What is the actual multiplier of PSL3-4?
It's Z mod 48. I think.
48.
Is it cyclic? Maybe it's, I guess maybe it's, I think it's cyclic. Z mod 48.
It's 48.
It's order 48, which is
awkward. Cool. Well, any other question for Carlos?
Yeah, here's here's a request. There was a lot of information in your talk. Would it be possible for you to make available your slides?
Yes, of course. Yes.
I'd
Yeah,
love to
I
have a
will-
copy of your slides.
yeah, I will send you to your mail, Professor.
Wonderful, thanks.
Yes.
Beautiful. Then Carlos, well, thank you very much, Carlos, for your talk and for organizing with all your Andres and Rita and Anna this session. Tell us now what comes next. I need to go back now. Noé.